Hello, students. Today we're going to talk about radiation, and we're only going to do just the key concepts and ideas from this chapter. I think it has a lot of practical applications in real life because so much of what you hear in the news is regarding radiation, whether it be nuclear disasters or nuclear weapons. So I think that this can be a helpful introduction to those ideas. We're going back in the past to talk about the nucleus. So, just a reminder that the nucleus is made up of neutrons and protons, and those as collectively are called nucleons. So, that gives the nucleus its mass number. And a nuclide is a nucleus with a particular composition. And so you saw this before in Chem 152 when you were talking about isotopes. So, for example, chlorine 35 and chlorine 37. So, just a quick review that if we want to designate or know the number of protons and electrons that it has, you would look up chlorine's atomic number, which is 17, and calculate the number of neutrons based on the number 35 and 37. So we'll see in a moment different types of isotopic notations, but that should be review from your earlier chemistries. So let me go ahead and I guess I can highlight it here. So chlorine 35, chlorine is Z number 17, chlorine 37. So for example, this one here, the 37, has 17 protons, and then that would have, therefore, 20 neutrons, whereas this one would have 18 neutrons. So recall that isotopes have the same atomic number, but differ in number of neutrons, which changes the mass number. And this might be the notation that you have learned before. So if you had chlorine 35, for example, the 17 is the Z number, atomic number, and A is the mass number, protons plus neutrons. You could also have, though, this notation used to designate on the bottom part, you're thinking of that part as charge, and the top part as mass. So when we write the electron down here, that is a charge of -1, and the top here is a mass of 0. Okay, so one of the important things that you should know for your quiz is that all the isotopes, the nuclei that are unstable, what happens with that concept is they spontaneously emit radiation, and that's called radioactive decay. And there are 3 natural types of radiation that radioactive elements emit. One are alpha particles. Alpha particles are identical to helium-4 nuclei, and there's 3 different ways that they're written. One is just the alpha. The other one shows alpha with the mass of 4. That's because it's helium. And the proton number or charge of 2, that's because it's helium. And then here it's shown with the actual helium showing it is technically helium 2 plus, but as you'll see on the equations we write, we're not concerned with the charge of it. So very rarely is it shown that way. Beta particles are another type of radiation given by the symbol beta. It could be beta written without any negative, one with a negative, or showing beta with a charge of -1 and a 0 mass. And that's because beta particles are high-speed electrons. And then gamma rays, do you remember from Chem 200, gamma radiation is a very high energy photon. And usually with gamma rays, it's given by the symbol gamma. Now, a couple comments. What we're going to focus on is what kinds of isotopes will emit, which type of radiation do they prefer? So that's one issue that we're going to talk about. And also what makes an atom unstable, that it emits radioactive emissions. Excuse me. When an atom decays, it forms what's called a daughter nuclide of lower energy. And when we write the decay process, we write a balanced nuclear equation. What has to be balanced is the total mass and the charge. This is going to be very easy. We'll see in a second. So, for example, one of our most famous radioactive atoms is radium 226. And it has, in this case, it decays to form and release an alpha particle. So if you want to stop for a moment and grab your periodic table, you can pause me because you're going to need it on this. You can pause me. Okay, so this is how this works. It's pretty easy. We're going to take the radioactive isotope, and we're told that it decays by alpha. So I'm going to write my alpha particle. And then I'm going to ask the question, what atom is formed? So I would say, okay, my mass and charge have to add up. So the charge has to be 86, the Z number, in this case, proton number, and the mass has to equal 220. Oh, that's a typo on that. That's not right. That's why I stopped. That has to equal 222, correct? So what I now do is I go look on the periodic table and I find the element that has a proton number of 86. So when I go to the periodic table, that's radon. Okay, so do you see how we have the release of this radiation? That's the radiation, the alpha particle. And then we form a daughter atom from the parent. Okay, couple comments. Alpha particles are very interesting because they are heavy particles because they're actually helium. So once inside the body, they can do a lot of damage. They don't penetrate skin though. So how would we go about getting alpha particles or alpha releasing radioactive elements in our bodies? Is we might ingest them through food, water, we can breathe them in. Once inside the body, they can do a lot of internal damage because they're just heavier. Okay. And what happens with radiation is these types of radiations are said to be ionizing radiations. Ionizing radiations can cause chemical changes, formation of what are known as free radicals. So for example, a good example of a free radical would be an oxygen atom. Well, as you know from your chemistry, that's going to look for something to bond with. So this can create a cascade of chemical processes, and there actually can be ramifications for our genetic code. So this type of radiation can cause mutations on a DNA level that can lead to what we think of are dangerous diseases like cancer. So, alpha particles, though, where would we get them? We're not going to necessarily run out to try to eat them, but if they're in a water supply or if they're in the food that we eat, then from an animal that's eaten or drank water from a water supply that has a high amount of alpha emitting elements, then that's where we can get exposed to them. Okay. In the case of, let's say, a nuclear accident, like the one that happened in Japan several years ago, they have that big plume of radioactive um, emission of radioactive vapors. So people that were in the area, if you're breathing that in at high concentrations, that's going to perhaps create very significant physiological effects. Okay, so, but we do need our periodic table to do the actual nuclear equations. And there was a little typo on that one because 222 plus 4 equals 226. So that's the mass being conserved. And then 86 plus 2 equals 88. Okay. Another type of radioactive decay is beta decay. So you have nickel here, nickel 63, that undergoes beta. So if I just write it pretending like that's not there. Okay, so let's ask the question, what number plus a negative 1 equals 28? So 29 plus a negative 1 gives us 28. So we go to the periodic table, and we see that copper is Z number 29. And then the mass, it has to be 63 because 63 plus 0 equals 63. So now we see that this particular isotope released a beta particle. Interesting fact here is that that is a high energy form of electrons. So your question should be, where did that electron come from, right? How could it be emitted from a nucleus? Because we know that electrons aren't there. So one way of thinking of this is the following. So I'm going to look at just the nucleus here. 28 protons for nickel. Then if I find the neutron number, I take 63 minus 28. So our neutron number is 35 for that original parent atom. And then this guy has 29 protons. And so that would make that 34 neutrons. So looking at it that way, do you see what happened here, which is a really amazing event, is that one of the neutrons, right, it went down in neutron number. One of the neutrons was converted to a proton. Do you see how it went from 35 to 34? So that's a neutron decaying. And then the proton number went from 28 to 29 because a proton was formed. And in the process of that transformation, an electron was made. It then is emitted at a high energy from the nucleus. So very fascinating. Okay, in a moment, we're going to talk about when an atom will do alpha, when it will prefer beta, but we'll get to that in just a moment. There's two other kinds of events that can happen in the atom. Going back though, let me just make one comment. A lot of times, these radioactive events are accompanied by gamma release. So the gamma radiation is an electromagnetic wave. It doesn't have mass or charge, and it's just a high energy photon. So that was our gamma. And a lot of times, the alpha decays and the betas are accompanied by that release of a photon. So we don't necessarily write equations showing gamma. Okay. Interesting point about gamma is that because it is a wave, It can penetrate skin very easily. But once inside the body, it actually would do less damage than an alpha particle because it is a wave, it doesn't have mass. I tend to think of alpha particles as being kind of a bulldozer within the body because it's just a much heavier particle and can find other species to react with to form those free radicals that then can create other chemical changes in the body. Okay, a couple more that we need to know. Positron emission. This is essentially what's called an antiparticle, which you might have heard of in like sci-fi movies. A positron is a positively charged electron. This is when a proton within the nucleus is converted to a neutron, releasing a positively charged electron. That's called a positron. So here's carbon 11 undergoing positron emission. If you notice now, I'd ask the question, what atom has a charge that 1 plus what number gives us 6? And that would be 5. And that's, if you look on your periodic table, is the element boron. And then what number plus 0 gives us 11 is 11. So that'd be boron 11. So what's happening here is that the nucleus converts a proton to a neutron and emits a positron. And then the last one is electron capture. It occurs when the nucleus interacts with an electron in a low energy orbital. And so here, this is the idea that you'd have your an isotope grab an electron and then form a new atom. And it's interesting because electron capture has the same effect as positron emission. So these two radiations, as we'll see in a moment, can occur in a radioisotope together, so that they're both seen for a particular isotope. And gamma emission, as I said, it occurs together with other forms of radioactive decay. It's just this high energy photon that's emitted. Okay, so this is a really handy chart. It shows the mode of decay, alpha, and it kind of tells you what's emitted. And so it's just a good summary of what we talked about. You can take a look at it more closely. I'll let you slow down if you have to. Okay. Okay, so let's just practice writing these real quick. I think you'll find them to be very, very easy. So that's good. So naturally occurring thorium-232 undergoes alpha decay. So first of all, I'm going to figure out which element's thorium, which is TH. That has an atomic number of 90. The mass number is given as 232. And then it releases an alpha particle. And now I say what number plus 2 gives us 90. So we go to our periodic table, and that is radium. And then I ask the question, what number plus 4 gives us 232, which is 228? And then I have there's my nuclear equation. Okay, next one, zirconium 86. So I need to find my atomic number for zirconium, which is 40. And it's going to capture an electron. I'm just going to show it as an electron capture, low-lying electron in an orbital. And do you notice then it's 40 plus a -1 is 39. So I'm going to look to see who has atomic number 39, and that's yttrium. And then the mass number stays the same in that case. Okay, so let's see if I got the right answer by clicking. Okay. All right. So those I think you won't have troubles with. They're pretty straightforward. Okay, now the question that should come up in your mind is which radioisotopes prefer which decay? Why are they radioactive to begin with? So the idea is the following, and I really like this picture. This is a reference, but this is a great slide, and this should be something that you look at closely. Okay, so early on in the periodic table from atomic numbers 1 through 20, so down here, 1 through 20, stable atoms have fairly equal numbers of neutrons and protons. So a good one would be our friend carbon 12 to talk about. 6 protons and 6 neutrons. So the ratio of neutrons to protons is essentially 1. And that makes it stable. So initially on the periodic table, we would say that the number of neutrons and protons are pretty much equal to have a stable atom. Remember that the nucleus contains a high amount of protons in a very small volume. Those guys should repel and the nucleus should fly open because like charges repel. That's the first day of physics to learn that, right? So there must be a stabilization of that, all those protons jammed in a small volume, and that comes from these neutrons. So if you don't tell your physics teacher, I think of neutrons as stabilizing the nucleus like a glue. It holds it together. They won't like that at your physics teacher, but I think it helps to visualize this. So neutrons and protons, initially, to keep the nucleus together, if you have 6 protons, then 6 neutrons is a good choice to maintain stability there. Now, interesting fact, something you learned in Chem 152 is that in nature, most of your sample of carbon 12 is carbon 12, about 99% of it, but some of it's carbon 13, and that's also stable. That has 6 protons and 7 neutrons. So our ratio of neutrons to protons, well, I'm going to see what number I get there. 1.2. That's still it is still stable. You do have in nature carbon 13, but the bulk of the sample of carbon is carbon 12. So they're not even in nature. Most of it's this one, but you have a small percentage that's carbon 13. Okay, so this then begins our discussion of this chart. You see the black dots. Those are stable isotopes. So looking up here, see where it says stable? It's a legend. So anything on this chart here that has the black dots, that's representing a stable isotope of that element. That's why this isn't a line, it's a belt, because one element might have more than one isotope that's stable. Okay, so if we're looking at carbon, just roughly, we're in this, there's 2 dots there for atomic number 6. Okay, everything stays with this idea initially that the neutron to proton ratio is around 1 or is 1, but then you get to atomic number 20 and you're still pretty good. But as you move beyond atomic number 20, the number of neutrons required to stabilize the protons, the amount of glue that you need, goes up. So what starts to happen is that our belt of stability starts to curve. It's not a straight line. And so if you look in this region here, here's iron. You have now an N to Z number of 1.15. As you keep going, you see how the N to Z, Z meaning proton number, 1.28. It starts to go up as the number of protons increases. You need more neutrons to keep an isotope stable. Okay. And the belt starts to really start to widen. So let's say if you look at atomic number 50, you start to have a lot of different isotopes for that particular element that are stable. Here, this is blown up. This section here is blown up over here. Very interesting. It's showing the stable ones in black for number 60. These are the stable isotopes in black. And then you're seeing when they're not on the belt, they are radioactive. So the main problems in this part of the periodic table is if you get too many neutrons, you go unstable. So too many neutrons, what that's going to mean is that you're above the belt of stability. And then you can also have the issue of not enough neutrons, and be below the belt of stability. So let's think about that. Looking at this blown up part of the picture, you have the dots here that are black. Those are stable isotopes. Above the belt, though, where you have too many neutrons, it starts to undergo decay. If you notice, though, above the belt, they all tend to do the same kind of decay, which is beta decay. So beta decay is the preferred route for an isotope that has too many neutrons. Okay, so that's going to be here when you have too many neutrons. The preferred decay is beta. And the reason why that is do you recall what I said to you before, is that beta decay is the conversion of a neutron to a proton and an electron. So what happens there is you're reducing neutron number. By undergoing that kind of decay, and it gets it closer to the belt or on the belt. It depends on what the process is, how far off the belt you are. Okay. Conversely, isotopes that are underneath the belt, they don't have enough neutrons, so they want to try to increase neutron number, reduce proton number, and so those guys are going to go beta emission or electron capture. So this is not enough neutrons. So how are you going to use this is very simply if you're asked, hey, what's this element going to do? Is it going to go beta? Is it going to go electron capture? You simply check this chart, and this chart will be available to you on your test, and it's a reference material. And you say, oh, okay, the isotope I'm looking at is above the belt, so it's going to go beta. If it's below the belt, it's going to go positron and or electron capture. As I mentioned to you earlier, those two events happen for a particular isotope together. Like they're two separate events, but it can have a certain percentage that's beta emission and another that's electron capture. It's usually not one or the other, but a combination of both. Okay, one other thing is that the belt stops. Really important to know this as a science student. The belt stops. Where does it stop? Is the last stable element on our periodic table, if you take a look at it, is bismuth, Z number 83. So bismuth 209 is the last one on the belt of stability. Beyond bismuth, starting with an element I think you've heard of in real life, which is polonium. Starting with polonium, you now have, those are elements that don't have any stable nuclei. What happens is they just get too heavy. So as I mentioned, initially neutrons and proton numbers are fairly equal, but as the elements get more and more heavy, too many neutrons, they need them to stay stable, but it gets to the point, and that point is atomic number 83. That's the last stable one. Starting anything beyond that, polonium, uranium, those are the famous ones. They end up with way too many neutrons. There are no isotopes that are stable, and they decay. What's the best decay? When you have a very heavy nucleus, the best way to drop mass is to do alpha. So above 83, so starting with 84, which is polonium, your best bet is to say those are alpha decay isotopes. Okay, so your uranium tends to go alpha, thorium. It doesn't mean always, but it just means that if you were to make a prediction, that's the best prediction. The other thing then to consider, one other thing that I think is important as a student of science is that radioactive elements do exist in nature. And so there is naturally occurring polonium, radon, radium, uranium. So these are naturally occurring. And let me just erase this for a second. So let's say uranium's a good one because that one's very famous. So uranium-238, uranium-235. These are radioactive and naturally occurring. So they do occur in nature. They're in the rocks. So the Earth has this natural radiation to it. Why are they still around if they decay? It's because we'll see in a moment, their half-lives can be ridiculously long, 100 million years for half of the sample to decay. So they take forever to decay. But I do think it's important to understand that after starting with polonium all the way through uranium, So polonium all the way through uranium. So polonium's atomic number is 84. These are radioactive and occur in nature. And because they're heavy, they do alpha decay as their preferred mode of falling apart and emitting radiation. After uranium, if you look on your periodic tables, the rest of those after Z number 92, those are radioactive but man-made. A physicist makes them in a lab. So starting with I'll say 93, Z93 and greater, those are man-made, and for sure they are unstable, they're radioactive. Okay, so to recap what makes isotopes unstable: too many neutrons. If the isotope is from an element from atomic numbers 1 through 83 and it's too many neutrons, it's going to prefer beta decay or beta emission. The other problems that it can have is not enough neutrons, not enough mass. Those go positron and electron capture. And then when they get way too heavy from polonium and above, the preferred mode is alpha decay. And then lastly, you can have naturally occurring radioactive elements that are only radioactive. They have no stable nuclei. None are on the belt of stability. Those are from polonium to uranium. And then after uranium, those are man-made and radioactive. Okay, and this summarizes that. Okay. So why don't you try this, and then you can just look at the answer on the slide. You're going to predict what happens to these, but what you have to do, you figure out where they're at on that belt, and then see if they are above the belt, below the belt, or above atomic number 83. So I'll let you do that, and then you can double check your answer on the PowerPoint. Okay, one other really interesting fact is that you can have a radioisotope like uranium-238, and that occurs in nature. It's in rocks, it's in the earth, so we can't avoid this radiation. And there are certain parts of the country that are more radioactive than others. So the Colorado area is more radioactive. There's parts of the Atlantic, on the Atlantic coast side, that are less. We're kind of at a moderate average range in California. But the uranium-238 will decay. And do you see here that it really prefers alpha? So you have alpha, all the red arrows are alpha decays. The other part here that I think is worth noting is that when it decays, it's not like it ends up stable. So this is what this is showing, is that it does a series of decays, producing another radioactive isotope that keeps decaying. There's some beta mixed in here, so there's like beta mixed in. Ultimately, it's trying to find stability, the atoms are, and ultimately the endpoint towards stability is at lead 206. So that's the ultimate goal, is to reach that stable nucleus. This can take literally what will seem like forever because the half-lives are so lengthy. They have very, very long half-lives. Okay, it's showing a radioactive Geiger counter. what I would like to just say to you is that the main unit of radiation and radioactivity is called the Curie, and it is given by disintegrations per second. So the becquerel is defined. It's the SI unit of radioactivity, disintegrations per second. And then the Curie is a more commonly used unit. 1 Curie is 3.70 times 10 to the 10 disintegrations per second as those nuclei fall apart. Okay, what I want to end on is where we started our journey together in Chem 201 is we started with kinetics. And kinetics is a good question here. How long does it take for these isotopes to decay? So the rate of radioactive decay is a first order kinetics. So this is exciting because we get to go back to review the idea of first order. If you recall, first order had the following: ln concentration of A at time t negative kT plus ln initial concentration. And then we also had the handy equation 0.693 over K equals T 1/2. If this is sounding not familiar, you need to go back in your notes and look at where we began with the idea of first order reactions that obey the first order rate laws. Remember, K was the rate constant. And recall that these integrated rate laws could answer the question: if I start off with a certain amount, how much is left over a certain time frame? The other thing here was the idea of half-life. Half-life is the time it takes for half the sample to decay. So remember that. And all of our radioactive isotopes will have a signature half-life. It cannot be accelerated. Temperature and pressure won't change it. So it is what it is. And so the only thing here, just to be aware, is that because we just talked about how they fall apart, disintegrations per second, the unit here isn't molarity anymore. It's going to be given up in the following way, but we just treat the equations exactly the same. So I wouldn't worry too much about the switch. What it's going to do is show it with regards to the activity. And so what will happen here is the idea that what is the half-life? That's the time it takes for half of the nuclei in the sample to decay. Okay, and the N here is really talking more about disintegrations per second as the units. So we're just swapping out molarity for a new unit, but the equation is exactly the same. It is going to be ln N of T equals negative KT plus ln initial. And the other thing is we still will rely on our handy equation for half-life for first order. So our radioactive isotopes obey first order kinetics. So let's see if we can answer a question. And I like this because it brings us full circle. We'll come back to that picture in just a second. Oh, I guess, okay, we'll do this. Carbon-14 is talked a lot about in terms of carbon-14 dating. So what happens is that carbon-14 has a half-life of 5,730 years. So the number of nuclei present every 5,730 years goes down by half. So we talked about this before of what half-life means. You start off with 100%. After one half-life, you end up at 50%. Another half-life, you end up at 25%. Okay, so every half-life, your sample drops by 50%. Okay, now why is carbon-14 brought up a lot is that carbon-14 is interesting. What happens is that all day long, when we're alive, we eat and we breathe. So we ingest food that has carbon-14 in it. So our food has natural radiation we can't do anything about. So we'll have a sample with food will have carbon-12 in it, carbon-13, and we'll also have a small amount of carbon-14, which is unstable and radioactive. It's actually made in the upper atmosphere and then gets involved in this discussion, which is called food cycle. So let's say picture that you have carbon in your, right, it's in glucose, C6H12O6. So, and a sample of sugar that we eat, some of those atoms are mostly carbon-12, but then you have carbon-13, you have carbon-14. So we're ingesting a small amount of radioactive carbon-14. Okay, all day long we eat, but then we breathe out CO2. So we release some of that carbon-14 when we breathe. So we have what's called a steady state concentration because we ingest but then we breathe out carbon-12. So we have a steady state, like a concentration of carbon-14 in our bodies as long as we're breathing and eating. But what happens when we die is that, I know it's a sad topic, is we stop eating and breathing. So the amount of carbon-14 that we're ingesting is no longer there. So that we have an amount in our body when we die, and then that starts to go down over time. So every 5,730 years, that is going to decrease. So what happens, how is this used, is that animals have a steady state concentration. The amount, let's call it 16, and that it has a radioactive unit, but let's just keep this simple. So what happens, if that's our steady state number, is that after 5,730 years, we end up with 8, drops to 4. So what this means is that, let's imagine that we find a bone of an animal and we measure how much carbon-14 is in that bone, then what will happen is we'll be able to figure out when that animal died. Because if the amount of carbon-14 is measured, let's say to be 8, so we get it here, that's our measured value, then we know that it died 5,730 years ago. If the measured value is 4, then we know that it died 2 half-lives. When it comes to carbon-14, the accuracy starts to go off after the second half-life. So normally the range of accuracy is in a range of about 11,000 years. Okay. if the amount of carbon-14 doesn't fall exactly on 8 or 4, that's okay, because we have our integrated rate law. So we can always solve for time t. And we know k because we have the half-life. So k equals 0.693 over 5,730 years. And so we can use that here. And then the amount of carbon-14 is measured when we find that bone, let's say. So we can solve for the time. And then that will tell us when that animal died. Here's some half-lives for beryllium's isotopes. They're all over the place, right? Some isotopes have very short half-lives. Some have very long half-lives. So you see here, this beryllium, this has a ridiculously long half-life. And so what we see then is that in nature, that's still going to be around because that half-life is a million years there for that guy. There's other ones with very, very short half-lives. And do you see the relationship here because of our relationship, our equation? The bigger K is, the shorter the half-life. So you see how this has a very big K value, and then the half-life goes down. We're going to finish on a half-life equation, just because come full circle. So strontium-90 is ingested by animals, and if a sample of strontium-90 has an activity of 1.2 times 10 to the 12 disintegrations per second, so this is our unit for radiation. What are the activity and the fraction of nuclei that have decayed after 59 years? And here's T 1/2. So whenever you're asked for how much is left, how much is consumed, we just say, oh, this is our integrated rate law again. And we are given the half-life, so we can find K. Okay, so we just essentially plug in and see. So this is showing that we're going to plug in our half-life. This ln2, that's the 0.693. And we get our K as 0.024 inverse years. And then now we'll plug in to our equation. So we're going to plug in, we're solving for the amount left. They switched units here, but it's okay. It could be N or A. I'll just be consistent with this particular slide. Negative K times T. This was given, the 59 years was how much is left, right, after 59 years, plus the initial number for the radioactive disintegrations per second. Just think of that. Think of it as just a different unit than concentration. So this was our initial radiation. And just like we did in the earlier chapter, which feels like a long time ago, we'll solve for what's left over. And this is that amount in terms of disintegrations per second. And the question asks for this is how much is left, right? And so I can solve for what fraction is left, because it just asked us to do that. So that should equal 0.24. And then the fraction then that was decayed would be taking 1 minus 0.24, which should be 0.76. Okay, so I think this is a good ending to say, hey, we can use first the kinetics to answer the question. I have a radioactive sample with a certain half-life, and I want to know after 59 years, in this example, how much is left. So this is a great application of kinetics, okay? And not all radioisotopes have the same half-life. Some have very lengthy and some have very short, okay? Okay, now one last comment. Here's just more information on the radioactive carbon-14 dating if you want to read. But one last thing that I think is really important is that radioactivity is really a natural thing that we're exposed to. So molecular interactions with radiation. So this was the free radicals that I was talking about. So whether it's gamma or alpha or beta radiations, they can result in the formation of free radicals, which is a species, like I mentioned earlier, that has an unpaired electron, and it's going to go on to react with things. And so what happens is that this can create a series of reactions in the body that can ultimately create mutations on a DNA level. And sometimes those mutations can lead to diseases like cancer. However, we can't be so afraid. We do need to understand that there's a lot of natural sources of radiation. There's cosmic radiation, the gamma and cosmic, not shown tonight, but was from Chem 200. Those occur from the sun, right? And those will increase with altitude so that when we, let's say, fly in an airplane, we're getting more exposure to those natural radiations. There's also radon, which is a radioactive product of uranium and thorium decay. Radon is a gas, and it contributes to about 15% of lung cancer deaths, but it's around us. It's a gas. It can be found underground. So people who live in the Midwest, when they have a basement, they need to pay attention to radon. And they usually have like radon detectors, because if you have an old home, you don't want that radioactivity to seep in, especially if you're hanging out there for long periods of time. As I mentioned earlier, we have food. Food has carbon-14. And then the other one is potassium-40, which is a good one to mention. Potassium-40 is radioactive. It's present in potassium-rich foods like bananas. And we do need to eat potassium-rich foods because our body relies on potassium as an electrolyte, but we're going to be ingesting some natural forms of radiation. So these are just some other ones. You can read this. I won't specifically ask questions on this, but just so you know, most of the radiation that we're exposed to is natural. Cosmic radiation from the ground, radiation from the air, which is mainly radon, um, radiation from daily intake of food with carbon and potassium. Okay, but adding on to this are artificial sources, which would be our X-rays, our flying around right on a jet plane, nuclear testing that occurred uh, has occurred that emits all those radioisotopes that take forever really to decay, long periods of time, right? Um, and so, anyways, so we shouldn't be afraid of radiation, but we should try to limit our exposure to more artificial sources. But certainly, if we have a medical emergency or medical issues, then the doctor weighs out, hey, we want to set. They have a broken bone. We want to set their bone correctly so they don't get sepsis, which is a blood bacteria. So we need to take them in for an X-ray, even though we know they're being exposed to ionizing radiation, but um, the benefit outweighs the risk on that. Okay.